right, everybody. Good evening, and thank you for coming to the Interstellar Research Group's 9th Interstellar Symposium public outreach event. Tonight, we're pleased to have the Interstellar Research Group's co-founder, Les Johnson, discuss some of his time as the author of many science fiction and science nonfiction books, but this one in particular is going to focus on his book, The Traveler's Guide to the Stars, considering some of the exceptionally hard problems that humanity will face in the road to development of proper interstellar missions. So, Les, I'd love to turn it over to you.
Well, I appreciate everybody who is from the conference who's here tonight, as well as any visitors we have from the community. What I'd like to do tonight is talk through a little bit of what is in a book that I wrote for Princeton University Press called A Traveler's Guide to the Stars. And the intent of that book was to convey to the average person who's not an expert in the field, and a lot of you have studied this field extensively, the challenges of distance and time, but also give hope. And as I think we've heard today in some of the technical sessions, there are really creative ideas about how we might really achieve interstellar travel sometime in the future. By way of background, if you want to bring up the title slide, my background is, you can tell I've been in the aerospace business for a while. I'm follically challenged here. I started out as a physicist right out of graduate school at Vanderbilt University in Nashville, working for a defense contractor in Huntsville, Alabama, which is now my home, and I was working on the end of Ronald Reagan's Space Strategic Defense Initiative, SDI, the Space-Based Missile Defense Activity. But my heart's always been at NASA. And I had tried to get into NASA for a job right out of graduate school and was unsuccessful. The fellow who had funded my graduate research worked at NASA. I thought I had a really good chance of getting a job in his department because he had an opening, but darn it, I didn't get in. So I took this job, and over time, as big events happened, like the collapse of the Berlin Wall and ultimately the Soviet Union, my wife said, you know, this whole defense thing is probably going to take a nosedive. Don't you think you want to try to get back where you wanted to begin with at NASA? And I did. So I've been working at NASA up until this summer for 35 years. I left as the Chief Technology Officer, and I had spent a lot of time working on advanced propulsion. Tomorrow I'll be giving a talk about the state-of-the-art of solar sail propulsion, which has been near and dear to my heart these last several years. But there's a whole gamut of different propulsion technologies. I'm also a science fiction reader. One of the reasons I chose the career of physics was basically reading science fiction. And the challenge of interstellar travel, I have found, is dramatically underplayed in the cinematic science fiction and in a lot of the books. And so what I'd like to do tonight in this talk is to try to put in perspective that we can relate to, which is very difficult, the challenges of distance and time, but not give up hope because there are ways that it can be done. Now, when this book came out, one of the things that I did to help promote it is I gave a talk, an online lecture at the Royal Institution in the UK. And it was shortly after COVID, and I really wanted to go give a lecture at the Royal Institution, but that didn't work out. So after Andrew Higgins today talked about how many hits his Universe Today talk got, I looked up my talk at the Royal Institution. It was over 500,000 views. And I've never had a video that's had 500,000 views. So I'm going to make hay on that on social media, just saying. But I was thrilled. So hopefully tonight you'll come away from this maybe thinking a little bit differently about the workshop, a little bit differently about the challenge of space travel, and have hope. I've got my contact information on here. I'll talk a bit later about some other books and some of the science fiction authors that are here in addition to me participating in the symposium. Have some of our books here for you to look at, and I'll talk about that more toward the end. The IRG, for those that aren't aware, many of you have been here all day. I'll just briefly recap this. This is our 9th Interstellar Symposium. It's a gathering of people who are serious about thinking about traveling to the stars. Not everyone's a scientist and engineer. Many are. But we also have writers. At this meeting and at other meetings, we now have had economists, space lawyers, philosophers, sociologists, people who are interested in governance of space colonies, We've talked about the ethics of doing this. We've had a meeting where we had 2 sitting congressmen attend to talk about their viewpoint in Congress and funding deep space exploration. We've had 2-star Air Force generals participate in previous meetings, and this gets a lot of attention. And we're having a great meeting here this week, and I'm going to move forward from there. This is a little bit about IRG. I've already just spoken to that, but I do want to point out, and I'm going to try out the fancy laser pointer thing here and see how well it works, that we do have a symposium next year that's going to be in Venice. We'll have another symposium in 27, which will be in the U.S., location to be announced later in the conference. IRG does provide graduate and undergraduate scholarships, and if I'm not mistaken, the opportunity for students to apply for that is open right now, that people can apply for those scholarships sponsored graciously by the Hampsons and by Bain Books in the Richard Bolgio Scholarship. We have a YouTube channel where all of our talks are available for public viewing. We have a podcast where we interview luminaries in the field, and they talk about their work on space and space exploration and interstellar travel. And interested readers can sign up every day for updates on the latest news from the world of technical publications for interstellar travel. So there's a lot here. We would encourage you to consider joining if you haven't done that already. So yes, just to begin, the title of my book is a riff on Hitchhiker's Guide to the Galaxy, and I think this one sentence kind of sums it up nicely. You just won't believe how vastly, hugely mind-boggling it is. I mean, you have to think it's a long way down the road to the chemist, but that's just peanuts compared to space, and that is an understatement. If you look at the interstellar neighborhood, which is a little bit misleading, you see the nearest stars, and they look kind of neatly arranged in distances of 1 light year here and 1 light year there. And if you read science fiction or the popular literature, you think, light years, okay, it's the distance light travels in a year at 186,000 miles every second. It's a long way. Well, we humans have a tendency in psychology that they call lumping. And in lumping, when things get big and small, the differences in orders of magnitude kind of go away in our mind. There are things that are big and vast, and how much more vast than they are than other things we kind of get lost in, and we just think it's a big number. And I think one of those things today is like the U.S. federal budget deficit, right? Most people kind of lump that, $1 billion here, $1 billion there, $1 trillion here, $1 trillion there. It's just a big number. And when we talk about distances to the stars, we're all guilty, I think, I'm guilty of lumping. And I look at this and I think, okay, 2 light years, and the galaxy's 100,000 light years across. It's a long way. Well, there's a big difference in those numbers, and I'd like to get a little bit into that. So let's talk about the nearest star system, Proxima Centauri. You can't see it with your eyes. It's a red dwarf star. But you can see the next closest star, Alpha Centauri, and if you haven't been to the southern hemisphere, you need to go. On our first trip to Australia, I dragged everybody on our tour bus out onto the deck of the cabin we were staying with at night to look at the Southern Cross and find Alpha Centauri, and I told everyone that was the target right there. And you could see it, and it was still a great thing to see. So if you ever go south of the equator, you need to look at that. But let's talk about this distance. Light traveling 186,000 miles every second takes over 4 years to get to us from Proxima Centauri. Now, what I like to tell young people when I give talks like this is that star is touching you, okay? If you were able to look through the telescope and see that, or you go out and look at Alpha Centauri like we did, or any star in the sky, think about it. Those photons of light left the surface of that star years, hundreds of years, thousands of years, and if you're looking at the Andromeda galaxy through a telescope, millions of years ago, have traveled across vast distances, and when you see them, that photon goes in your eye, and it touched you. Something that had traveled for millions of years, maybe, touched you across interstellar distances. And when it left that star, it was on its way to your eye. I mean, that's amazing. We're touching the stars when we look at them. It's just incredible. But what do these distances mean? 1 light year is 5.8 trillion miles. Proxima Centauri is about 25 trillion miles. What does that mean? Well, I'm going to put things in perspective that kind of helps me parse this. And when I've given this talk to people who are non-experts in the field, I think they come away with a better understanding. So let's talk about our solar system. The Earth to Sun distance is 93 million miles. It takes 8 minutes for light to get here from the Sun. We're going to shrink that distance down, not to one astronomical unit like astronomers do, which is their term for it, but we're going to call it one of Les's New Balance shoes. I'm a size 11.5, which means my foot is almost exactly a foot long. So from heel to toe is 1 foot. So if I'm standing up here at the podium, from the heel, if it's the Sun, to the tip of my toe is the distance from the Earth to the Sun, Sun to the Earth, 1 foot. On this scale, if we were to put the solar system in this room, the furthest planet would be Neptune, and it would be 30 feet away, which is roughly the back wall of the room. It takes our spacecraft 10 to 15 years without having advantageous flybys to cover that distance. That's a long time. That's a long way. But how far away is it really then to the nearest star? On that scale, where every foot I have of my foot is 93 million miles, the nearest star to where we are today is over 50 miles away. 50 miles times 5,280 feet times 93 million miles is the distance to the nearest star. OMG. That is the closest star. How are we ever going to do that? That's 2/3 the distance from here to San Antonio. Okay? That is a long way, and that's the closest one to us. If we want to go to where all the good stuff is, like Vulcan or something, we're going to have to go farther distances, and those distances are not measured in tens of light years. They're measured in hundreds, if not thousands of light years. This is an artist's perspective of what our galaxy might look like if we were outside looking in, and from one side to the other is roughly 100,000 light years across. We've got a long way to go. And then we have the 1990s. Prior to that, astronomers suspected there were planets circling other stars. We science fiction readers knew it, right? Because we were reading about it. It was in science fiction. It was commonly known. However, there was no scientific evidence that there were planets circling other stars until the 1990s. Those of you who are younger may have trouble realizing that. But there was no confirmed exoplanet until that time. And after that, there were, by various methods, the confirmation, physical detection, observation, either directly or indirectly from their effects, of planets circling other stars. Today, in this little region of space that we've been able to observe, which you see right here, we have found over 5,200 exoplanets confirmed. That number is probably closer to 6,000 today. And that distance is really small. It's our planetary neighborhood. So I get asked a lot when I talk about space travel and going to the stars, what's out there? Well, the answer is there are a lot of planets out there. The next question is, well, how do we get there? How are we ever going to do that? Well, as was mentioned in one of our talks this morning, we have already sent our first probes to the stars. The Voyager spacecraft launched in 1977. I was alive. I remember when they were launched. I remember staying up late when Voyager 2, I think it was, flew by Neptune, and public television had a 24-hour viewing of live images coming back from space, and it was called Neptune at Night. And I remember staying up late with my wife to watch this as the images for the first time ever were coming back from Neptune. But the plucky Voyagers continued onward, and they're out in interstellar space. They're beyond the heliosphere, the influence of our sun. That's where the outward radiation pressure from the sunlight is roughly balanced by the inward radiation pressure from all the other stars in the Milky Way. The gravitational influence is still there, but the solar wind and all that influence has kind of died off. But if they were going in the right direction, which they're not, they would reach the Proxima Centauri system in about 74,000 years. So we are already an interstellar species. We have sent our first emissaries to the stars. New Horizons is not far along. And all of these have been launched with chemical rockets. Well, the question then comes up, can we go faster using chemical rockets to reduce that trip time? Because that is not a practical trip time. And so I'm going to give you a definition of practical trip time that I used in the book that at least one science fiction writer, David Weber, said he really liked. And that is 1,000 years is my upper limit for practical interstellar travel. And why do I say that? Because I have traveled the world and I have seen remains of buildings that are over 1,000 years old. I have seen buildings that are still standing in large part that are 1,000 years old. There's one in the West Bank in Israel that King Herod built 2,000 years ago, and it is still standing. Okay, I was in it just 2 years ago, 3 years ago. So these are out there. The cathedrals of Europe took centuries to complete. The Great Wall of China took centuries to complete. These were human endeavors where people had an idea of something more important than themselves that would take out of their lifetime to see to fruition, and they did it. So I would contend if we can get the trip time to the stars to be under 1,000 years, we should begin undertaking those voyages and know that 1,000 years later, someone's going to turn on the detectors to get the images of the instruments back, even if we launch faster probes later. It's an endeavor worth doing. But chemical rockets will not be able to do that. And that's because there's only so much energy you can get out of making or breaking chemical bonds to release energy. And that includes all the way from the Saturn V to the NASA's SLS to the Starship, which did it launch? It did. Successful launch. Excellent. The booster landed successfully in the Gulf, and they're checking on the ship. The thing to know is, no matter how great that rocket is, it's not efficient enough to carry enough fuel, to carry the weight that would be required to carry all that fuel, to get us to the stars in any faster time than 72,000 years. It is not going to happen. So they're too inefficient. Now, for propulsion, scientists don't use miles per gallon, kilograms per liter. They use something called specific impulse. It's measured in seconds. Don't worry about that if you don't want to go into the math. It's basically a measure of the efficiency of the engine. The higher the number, the more efficient it is at converting propellant into change in velocity to make trips faster. Rockets top out at a few hundred seconds of ISP. Electric rockets are a great advancement, and instead of using chemical energy, they use electromagnetism to accelerate the rocket propellant to give the spacecraft propulsion. They're low thrust, but they're extremely efficient. They're between 5 and 10 times more efficient than a chemical thruster. But that's still too inefficient because it doesn't get us down to my arbitrary, but based on history, number of 1,000 years. Electric propulsion, if we build a system, nuclear electric or something like that, that was extremely efficient, we might be able to get down to 10 to 12,000 years. That's still too long, not very practical. There's been interest in nuclear thermal propulsion. In fact, I was on a panel at a science fiction convention this weekend about nuclear rockets. They're great. We need them for Mars. I could talk for hours about how important they are for human exploration of the inner solar system, but their efficiency is only roughly double that of chemical rockets, not even close to what electric propulsion is, too inefficient. So none of these rockets will get us to the distance we need to go in the time frame we have. Now, there are some that might, and we've talked about many of these today, and I'll go through these somewhat quickly. One is nuclear fusion. That was mentioned today about the feasibility of a fusion propulsion system, trying to figure out how to mimic what the sun does to produce energy, doing that compactly, put it on a spacecraft, go. The scale is enormous, but it's possible. So if we get fusion power perfected here on the Earth, the next step for the engineers is to miniaturize it, put it in a spacecraft. We could send a probe to the stars, nearest stars, with a trip time of about 1,000 years. Now, what's exciting about that is nature has said there's nothing fundamentally preventing you from doing this. You engineers just figure out how to do it, right? The physics will allow it to work, which is great. People ask about Project Orion. I have so many stories to tell about Project Orion. Project Orion is a really cool idea that's a really bad idea that was derived at the end of, near the end of the Cold War, real hot, potentially hot part of the Cold War in the 60s, 50s and 60s. A group of engineers, including the famous Dr. Freeman Dyson, who's pictured here on the bottom right, I have him circled there, they came up with the idea that if you take a big spacecraft, think a battleship, or a submarine, and you put underneath it a big plate. Think a big steel plate that's the height of this ballroom and the width of the first floor here, and big shock absorbers between it and the spacecraft, and start dropping a small nuclear weapon underneath it every 3 seconds, that you could get enough thrust to reach Alpha Centauri at some fraction of the speed of light. The answer is, theoretically, you could. Yes, that would give us a very large interstellar spacecraft, and you would probably destroy the biosphere or damage it pretty greatly as you go forward to do that, and it's not likely to happen. I will say, though, that, let me give you, there's a video. Can you play the video at this point? This is a non-nuclear test that was done by Freeman Dyson and his team with conventional explosives, showing that you can actually get thrust from this to propel a vehicle. In the Cold War, the idea was that we would have space battles with space battleships, and if we didn't launch ours to the scale I just talked about, those Ruskies would have done that, and they would have controlled space, and we would have been out of luck. So this whole premise behind this was for defense purposes. But when you looked at the math, you realize, you know, we might be able to get to the stars in under 1,000 years with people doing this. Not something I think we'll be doing anytime soon. I have a story about Freeman. I met him at Caltech at a meeting talking about interstellar travel, and he was our eminent speaker. He was getting older at that time. He was invited in to give the lecture. We were a 3-day workshop. He was running a little late. The organizers of the event at Caltech read us the riot act. Do not bring up Project Orion. He is embarrassed by that, and he will not want that talked about in this meeting. So we all said, okay, that's fine. So Freeman came in, gave a great lecture. He stayed for the entire week. It's the last day of the meeting. It's lunch. We had our boxed food come in. I'm having my boxed lunch. Guess who sits down right in front of me? Freeman Dyson. I'm a fanboy, all right? So I said, oh, Dr. Dyson, I'm glad you sat down. How are you? We chatted for a minute, and I looked around the room. I'm not normally a rule breaker, as my wife will attest. But I said, you know, I really was excited when I was younger about reading about your work on Project Orion. The man lost 10 years of age from his countenance, burst into a big grin, and started regaling us with stories of how they tested Orion with these non-nuclear explosives, and actually had pilfered explosives on some Navy base, and had to like appeal to the commander to not have them all arrested and the military guys that helped him. And before I knew it, everybody in the room was gathered around listening to this story. So the moral of the story is, unless you're a student, it's okay to break rules sometimes. And I don't normally do that, but it was great, and I was really thrilled to hear that recounted from none other than Freeman Dyson himself. It was a great thrill. However, I don't think we want to build that. Now, this is one of my favorites. I'm a Star Trek fan, I'll admit it. You can guess what happens to the poor guy in the red shirt. But this is where they had to, Kirk and his team had to build the antimatter bomb to get rid of an entity that was like killing all these people on the planet. And the only way they could kill it was through antimatter. Well, I want to tell you right now, antimatter is real. Antimatter is produced in nature all around us. High energy cosmic rays come zipping into the atmosphere at close to the speed of light. They hit the atmosphere. Particle collisions occur, and these weird particles called antimatter are produced. This is not dark matter, this is antimatter. Particles that just look like electrons that are called positrons. If you're a science fiction fan, you know that those are important for our future robot overlords, and they're positronic brains. Then there are also the antiprotons, which are more massive. You can take an antiproton and a positron and make antihydrogen. Really cool stuff. The difference is the electrons, instead of being negatively charged, they're positively charged. And the protons, instead of being positively charged, are negatively charged. There's also a spin state that's different, but that's not really relevant to where we're going with this. And a neat thing happens when you put the two together. When an atom or an antiproton and a proton collide, they annihilate according to E equals mc squared. And all of their mass is turned into energy. And gamma rays, muons, all kinds of secondary particles come out. It is the most efficient battery nature will ever allow us to build, okay? The nice thing about that is, if you can get enough of it and store it, which is the challenge, because getting a perfect vacuum is almost impossible, and having magnetic fields to keep these charged particles from touching the walls and annihilating in whatever's containing them is really hard. And if you have enough of this and it collides with normal matter, like 10 milligrams of antimatter will explode with the equivalent force of 120 tons of conventional rocket fuel. This could be a terrible bomb. Don't go see the movies believing that, but it could be a bad day. But if it's produced in space and we store it well enough, it could be the energy source that gives us the stars readily, but it'll be expensive to produce. The total global output today is on the order of nanograms, and we need to have kilograms. In fact, we need about a metric ton of it. Now, at this morning's lecture, Andrew Higgins kind of stole some of my thunder, but I'll tell you all anyway because I think it's a fun fact. Bananas are grown in soil that's rich in potassium-40. Every 70 minutes, that radioactively decays in nature and produces a positron in the banana. So if you had a banana that was out on the table there today, going through your gut right now is an antimatter factory producing a particle of antimatter about every 70 minutes. It's annihilating, and it's not going to disturb you. It's just part of nature and the natural background that we have. I actually had someone, after I gave this lecture somewhere, actually calculated how many tons of bananas we would need to build our antimatter system, and it was an unbelievable number. But don't be afraid of radiation. It's a fun fact. Is there another way? Yes, there is. And I'm going to take a little bit of time to describe what has been my focus over the last few years, and that is forget about rockets. All these systems I've talked to you right now are huge, they're heavy, they require a lot of fuel, it's complicated to make it work. There might be less complicated, I'm not going to say easy, ways to get to the stars that do not involve rockets. And for me, that's been the work lately on solar sail propulsion. Now, solar sail is a large, lightweight, reflective sheet, and it just so happens I carry a propulsion system in my pocket, and I have a piece of solar sail here, which is the same material we have flown in space to fly a solar sail. So imagine this lightweight material unfurled over a large area. It's very reflective. It's coated with aluminum. It reflects about 90% of the light that hits it. And photons, as they travel through space, do not have rest mass, but they have momentum. So if you think of photons as little particles, and they hit this, they bounce off, they lose a little bit of energy. For the physics-minded among you, they're redshifted, so we have conservation of energy here. And that momentum is transferred to the sail, and it will push it. And if it's a light enough sail, with a light enough spacecraft, not massive, very large, lightweight sail, you can get propulsion. Now, you can use this to maneuver in the solar system, which has been demonstrated in space by my team and others, and you can use it eventually to reach the stars. The scale, however, is enormous. But I would contend it may not be as challenging in terms of engineering to build the sails we need as it would be some of these other technologies. There have been several sails flown. I'm giving a more detailed talk on this tomorrow, so I won't go into a lot of the details tonight. But I will say that over the last 2 decades that I've been working at NASA, I have been the lead for most of our solar sail work. We did some ground deployment tests of a 400 square meter sail. We flew a 10 square meter sail in 2010 in Earth orbit. That technology spun off and was used by the Planetary Society to fly 2 32 meter squared sails. And they basically used our design and improved the efficiency. I was the principal investigator for the Near-Earth Asteroid Scout, which launched in 2022 to deploy an 82 square meter solar sail. And the last one on the right is to scale, and it used to be called the Solar Cruiser. Solar Cruiser was put on ice for a problem with the spacecraft bus, and I'll describe this in detail tomorrow, but it has been reborn. It will fly in 2029. It's got a launch already labeled. I'll be going back to be a consultant on the project because it's been my baby in my career at NASA, and I'll be going back probably sometime next year to help out with that. But this thing is 17,800 square feet, and it's the thinness of a hair made out of this same material. And it's not going to the stars, it's going to the Sun-Earth L1 position to study the sun. So they're real. This is a picture of a test of 1/4 of that sail as we deployed it a few years ago at NASA Marshall. And if you look very closely with a magnifying glass, the third person from the right is me, there for the day with the test with the engineers who did the deployment. It's deployed with 2 booms that are 100 feet long. You can see those there, made out of composite. And the entire 17,000 square hundred-foot sail fits on this spool, and the booms all fit in this box, and it bolts to a spacecraft, and it's ready to go. Now, if you speak delta V, those of you who understand what I just said know who you are. A solar sail like this will give you 3 kilometers per second of delta V per year of operation. Most rockets will give you 100 meters per second over their lifetime before they run out of fuel. So it's a lot. This is a roadmap I put together years ago about how we should develop solar sails to go to the stars. And it's not Moore's law, it's Less's law of solar sails, which is that every sail increment is an order of magnitude larger than the previous one. We flew a 10 square meter nanosail D in 2010. We developed the NEA Scout almost 100 square meter sail and the ACS-3, which is in orbit right now, which is almost 100 square meters. It's 80 square meters. We have developed the solar cruiser sail, which is 1,000 square meters. It's actually 1,600 square meters. Its design is scalable to the next one, which is 10,000 square meters. So in 10 years, 15 years, we've gone from 10 square meters up several orders of magnitude in size. We only have 2 more leaps until we have the sail we need to do an extrasolar mission. Now, there is an alternative approach to sails that I'll briefly cover before I talk about a few other issues, that you could use augmented light with lasers to propel sails. I am not a fan of the breakthrough starshot approach. There are too many miracles to build these little micro spacecraft and these sails to fly them to the stars. I think what we need to do is build square kilometer scale sails, say that 5 times rapidly, as I have here, and use big lasers to add extra energy to them to go to the stars. This idea was first put forward by Dr. Robert Forward, one of my mentors, and he had laser power stations in space that could continually focus laser light to accelerate these out of the solar system at up to the speeds of 10% the speed of light, making the voyage to Alpha Centauri in under 100 years instead of 1,000. Now, when I did this roadmap, we had this material, but if you did the math for that square kilometer sail, you would find we had nothing light enough and strong enough to sustain its own structure under the tension that would have to be applied to keep it flat and lightweight. We needed a material that was a single atom layer thick, that was strong enough to support its own weight, quote, under tension to go to the stars. No material existed in the year 2000 that would do that. And then in the year 2004, 2 researchers in the UK discovered a material called graphene. I'm sorry, what was that, Stephen? They stole it from Georgia Tech, says the Georgia Tech guy. Not to impugn your credibility, but of course. Okay, well, I hate to tell you this, they won the Nobel Prize in 2010 for the discovery of graphene. And it was one of the eminent scholars in our field who was the first to realize that graphene could make this square kilometer sail, and that was Dr. Greg Matloff, who's not here with us this week. Greg published the seminal paper on graphene solar sails. It was that paper that inspired me to reach out to Joe Meany when he was still a graduate student at the University of Alabama. I said, hey, Joe, you want to write a book about graphene? And we did. My agent sold it to Prometheus Books, and it was then published and actually did really well. Joe and I, it was cited in Nature and excerpted in American Scientist and all this. But the point is, we now have the material. We did not have it when I put that roadmap together. Now, the problem is the engineers, again, haven't figured out how to make it a square kilometer. They can make a few square centimeters of pure graphene at best, and we need square kilometers. But it can be done. There's no fundamental physics that says it can't be done. So let's assume we're wildly successful. We shine a laser. Oh, by the way, I'm not covering speculative physics, okay? That's not in here tonight. I'm not covering Alcubierre warp drive. It requires a form of matter that we don't know exists. I'm not talking about the EM drive because it's not real. And we'll just put those off to the side, and you can keep clickbaiting them whenever they come up on your news feed. They're not real. But let's talk about success. Let's assume we are successful beyond our wildest dreams. And we build a starship, and we're sending it off to Alpha Centauri, and it's traveling at 10% the speed of light. And let's assume that our success has allowed us to miniaturize that spacecraft to a realistic size and could carry cameras and instruments to beam stuff back. And it's not a gram satellite like Breakthrough wanted to do. I'm going to be generous. It's a kilogram spacecraft, 2.2 pounds. And lo and behold, I love fruit. So when you go to the grocery store, there's another example besides a banana for antimatter. It can be a pineapple for the size of our spacecraft to go to Alpha Centauri. So I'm not trying to miniaturize things as much as the Breakthrough people did. I'm trying to, engineer something smaller. It'll be a challenge, yes, but let's assume our spacecraft is 1 kilogram, the size of a pineapple, and we fire it off to Alpha Centauri. Now, as we heard in a talk today, our aim has to be really good, right? What was the uncertainty in the launch angle? What was it? Millionth of a degree. And we still have an uncertainty of 400,000 kilometers at the other side. Let's assume we get close, but not quite perfect, and instead of flying by Alpha Centauri's planet system, we hit one of the planets with our pineapple, traveling at 10% the speed of light. We would have just declared the first interstellar war, because that pineapple would explode with the equivalent energy release of 9 Hiroshima-class atomic bombs, just from its kinetic energy and its motion, okay? So when we're talking about interstellar travel, we are talking about energies which are immensely farther beyond what we're accustomed to dealing with. And herein lies a problem with a lot of science fiction, right? They're wondering how they're going to destroy that enemy, and they're flying faster than light. Duh. All you do is take one of your faster-than-light spacecraft and aim it at them, and you can take them out, right? So it is going to be something that we have to be really cautious of and think about, because these are enormous energies. And it also brings to mind the unlikelihood that we're currently being visited by beings traveling within known physics using these craft. But that's another talk altogether. Now, another question that comes up, and it came up today, is why send people? Why don't we just send our robotic emissaries? And is it going to be robots, people, or both? That question was answered very convincingly for me at another meeting. I have stories for everything, all right? I was at a meeting I just gave away the answer. Let me go back quickly. At Mars meeting, talking about future of Mars exploration. And it was a group of Mars scientists, and this was at the Lunar and Planetary Institute in Houston, near Clear Lake, near the Johnson Space Center, trying to reformulate a Mars program. This has been 15 years ago. And there was a panel discussion to kick off the conference where all the people from JPL were arguing, we don't want to talk about sending humans to Mars. It's going to be much better just to send our robots. Why bother with people? They're big, squishy things, require lots of things to keep them alive. It's going to be really big. It's going to be really expensive. Don't do it. The other side of the room were all the people who wanted to send people, human exploration advocates, who were saying, yeah, but, we want the human experience, all the things you might expect. And it was real interesting. It was like this room. The audience was out here, the panelists were up here. But in the middle right here, facing the panel, was a chair. Nice chair, comfortable chair. I just thought of Monty Python, the comfy chair. And sitting there, and it had a name tag on the back of it. And that name tag was 4 letters long, and that was Buzz. So you can imagine who that was, Buzz Aldrin. Well, Buzz doesn't come in at the beginning of a meeting. He comes in 5 to 10 minutes after the meeting is underway. And it's like the old E.F. Hutton commercial, when Buzz Aldrin enters the room, everybody gets quiet. So here comes Buzz, he looks around, he sits down, he's got his own chair, it's got a name on it, they're arguing this thing. After about 5 minutes, he stands up, and he stops, and everybody stops to listen to what he says. And he says, how many of you would sign up, if I could give you certainty, that you would take a one-way trip to Mars, that I could get you there. And 60% of the people in this room raised their hand. I didn't. I'll so go in a minute. 60%, including about half the people from JPL who had just been arguing, only send the dang robots, okay? And his point was, which he made, is that it is not we're going to send people or robots. It's we're going to do both. We're going to send the robots first and then the people. And if you look at the history of our space exploration, it has been that way all along. We sent Sputnik and Explorer 1 before we sent Yuri Gagarin and Alan Shepard. When we went to the moon, we sent the Lunas and the Surveyors. Then we sent Neil Armstrong, right? So we're going to send the robots, then the people. So I thought that was the best way to look at this, and an approach that I agree with. It's senseless to argue otherwise, but the robots will be first. It'll be both. So to conclude, one of the questions that I get asked, and actually it came up today in a paper that was presented about how to come up with the society that will be sending people to the stars, and it was loosely an economics-based argument. And I don't look at it in economics. I view, and this is Les's personal moral compass and philosophy, I view the exploration and settlement of space by the human race as being a moral imperative. And I deeply, deeply, deeply believe that. And the reason I believe that is as we've learned more about space from Voyager and the spacecraft we sent to all these planets, and we look at all these exoplanets, it is clear that the majority of the real estate in the universe is dead. It has never had life. It never will have life unless we take life to it. And I also contend that life is good. I think if you look around at the crap we humans do, you have to agree we do that. We also create symphonies. We also make babies and children, and the love of a parent for a child and a child for a parent is inherently good. Looking at the Mona Lisa, looking at the great cathedrals of Europe, looking at the Great Wall of China and those achievements, that is something that is morally good. And I contend that life from the bacterial level all the way to humans and all of that in between is precious and rare in the universe. And the Earth is a place we need to preserve and protect and have space help do that. It's a topic of my next book, by the way, from Princeton Press, that'll be coming out next year. And we need to be looking at how we extend life beyond the cradle, as Arthur C. Clarke said, because you can't live in the cradle forever, and something might happen to the cradle either at our own hands by accident or that nature might whack us. And when I look at space and I get the common argument in rebuttal to what I'm just saying, which is we'll just trash it. You know, what right do we have to go and take our stuff there? We should leave it a pristine environment. I will argue the reason we are concerned about keeping the environment pure is that's where life is. The moon is not an environment. The moon is a deadly place to be that will kill you instantly if you're unprotected. Life is not going to arise there. Life will never arise there. It will only go there if we take it there. And that will be a moral good, okay? So I believe that we've got to do this. I think it's not only something that is the explorer's imperative. You may have your own reasons for thinking we ought to do this. I think we need to do it for the protection and preservation of the human species. I think we need to do it because it is the morally right thing to do. So with that, I'll stop. You've heard me preach for the evening. I guess I'm the interstellar preacher. But please give me any questions you have, and I'll be glad to answer those if you have any, or I'll try to. And if I can't, you can bet we have somebody in the room who can. Anybody have a question?
Are you saying that if we find life on another planet, we will shut down our own search? and travel?
Okay, I actually I address that in the book, and I'm asked that question a lot. I really love the Star Trek Prime Directive. And that notion is, in my personal opinion, but I also see the other side of this debate, which I'll make in a moment. If we go to a world somewhere in our solar system and beyond, and we find life that does not have its origin on Earth, but extant life that's different there, I believe we ought to preserve it and protect it and not destroy it, absolutely. However, I believe it was Jerry Pournelle, make an argument which was really hard to refute. And that argument was, well, wait a minute, who gave the scientists the right to veto the rest of the human race in terms of what we're going to do in space exploration? And I didn't have a good answer to that. And so, you know, if it's up to me and I'm in the chair making the decision at that time, I'm going to say, no, we're not going to mess this up. We're going to let it do its own thing. Let's go somewhere else. There's plenty of other dead real estate to go to. But I can also see the argument of people saying, well, wait a minute, you know, this resource is there, it's better for humans, let's just go ahead and do it. What gives the scientists the right to veto that? I can see that argument. I don't agree with that argument. But I would have a prime directive. Does that answer your question? Yeah, that's my personal opinion.
I do not feel like you have plugged your work enough. When will your next book come out, and where can we find the rest of them?
Well, I'll do the plugs of the books here. I also write science fiction, primarily for Baen Books, and my latest novel is the second book in a series called Crisis at Proxima. It comes out in paperback in about 2 weeks, if I'm not mistaken. It came out in hardcover last year. If you're here at the Symposium, you got a copy of the first book in the series, Saving Proxima. And Travis Taylor and I are working on the concluding book of the series now and hope to have it submitted next year. Don't hold me to that. It's the intent, but I don't know about that. Yeah, Tony's not here to hear it, so I guess she got away. Another of my books up here that I wrote a couple of years ago called The Space-Time War, which is my foray into space opera, if you're into science fiction genres. But I'm also real excited. It's not a Baen book, but on November 4th, Tor Books is publishing a novel that I wrote called Pluto. And if you've been in this field for a while, you know about the great science fiction writer Ben Bova. Ben is one of the, I call him the deans of science fiction. He's a Hugo Award-winning editor, has 5 Hugo Awards. He passed during COVID, and his widow reached out to me and asked me if I would complete Ben's last novel. And so I did. It's called Pluto. It'll be published by Tor Books on November the 4th, and I'm really excited about that. It's my, I tried my best to honor Ben's spirit in concluding this book and the Grand Tour series. I will tell you, however, he didn't give me a lot to go on because he was what's called a pantser, in that he did not have an outline, and he'd only written about the first 6,000 words of the novel. So I have no idea how Ben would have ended the book and the series. So I went back and reread the last several novels in the series and gave it the best possible conclusion that I could give it in honor of Ben, trying to think about how he would have done it. And I hope as he looks down upon us now, I hope he's okay with what I wrote. And equally importantly, I hope that the Ben Bova fans out there that read it don't start throwing rocks at me. But I hope I honored that. And then I have another book, my first urban fantasy novel written with Larry Correia in the Monster Hunter series, which is in development right now. I finished my part, Larry's working on it. Hopefully that will get to Baen next year. And I'm also writing that book for Princeton Press about how space technology can help solve energy and environment problems here on Earth. And I've got the first draft of that finished and ready to go to Princeton. So, is that a plug enough? Okay, great. Oh, by the way, I have to plug a fellow author's book, Rob Hampson. Rob, raise your hand. Rob's also a working scientist, a different field. He's an expert in brain science, and his novel, Moon in the Desert, is up here. It's a great read. I would encourage you to read that too, especially if you're fans of the old series, The $6 Million Man. It's an updated take on that. So Rob's written several other books that are not represented here. The bet is in the audience. And Bill Ledbetter, are you here with us somewhere? Bill Ledbetter is a Nebula Award-winning science fiction writer. He's had several great stories and books sold, and you can find him pretty widely distributed also. So we have just a couple of minutes if there's any other questions or thoughts. And yes, if you want, you can come see the solar sail after I finish. Yeah.
You discussed the Great Wall of China, the cathedrals, all those things have connections to a threat or a religion. On the concept of Jerry about the scientists don't get to decide, the society should. How do we motivate a society to want to do interstellar travel? Do we need a threat or a religion?
They need to come to the IRG Symposia. They need to watch our YouTube channel and see all these talks. They need to read our science fiction books. That is a difficult question to answer. Most people, just quite frankly, don't pay attention. And I've often said, and this is wishful thinking, if nobody were to get hurt and the power would go out and people went outside, away from their phones and their computers and their televisions, and looked up at the sky and saw the Milky Way, which a lot of people have never seen, they could not help themselves but ask the questions that our ancestors asked. What's out there? Who am I? Why am I here? And what's my relationship with what's out there? That gave rise to religions. It gave rise to the science of astronomy. And it gave rise to what we're doing here in this room. We are trying to make that connection with what's out there. And there's ways to do that in your faith journey, which I have a separate faith journey from this. I am a Christian, and I believe there's purpose in life. I also believe that there is a calling on all of us as we look to the stars to wonder, wow, what's out there? And I think if we could have this community event of black out and look at the stars, some for the first time in their lives, ask people that you know, especially young people. They may not have ever seen more than a handful of stars that they have trouble seeing because of the street lights in the city they live in, right? But you go out in the desert or the Grampian Mountains in Australia, where we were when I was pointing out Alpha Centauri, and you look at the sky, you can't help but have those thoughts. And I think funding and support for space exploration would go up dramatically, as would church attendance, quite frankly, if people did that, because it would give them a taste of something bigger than themselves. I believe that. All right. Thank you all very much.